Allora ragazzi, andiamo subito al prossimo ospite. I'll maybe switch to English because this is our first international guest, I guess. Yiannis Stavrou, is that correct? Is my
Yeah, that's
pronunciation?
correct. Nice to meet you. Nice to be here. Glad to participate.
Yiannis is a security researcher in the operational technology with experience in the PLC forensic analysis, protocol reversing, and anomaly detection. And he will tell us about a long-range disruption of industrial processes using drones and LoRaWAN. Thank you so
Absolutely.
much, Yiannis. The stage is yours.
Thank you so much. Right. Hello, everyone. Nice to be here. I'm Yiannis Stavrou. I'm doing vulnerability risk analysis in Nozomi Networks. In this presentation, we are going to discuss a bit about LoRaWAN. So what we wanted to do was to understand how we can rethink the challenging of this protocol in the industrial format. And we think that while there's a lot of advance in this technology, there is still a lot of nice ways to disrupt it. So let's get started. So a bit about LoRa. LoRaWAN is categorized under the low power wide area networks. This is kind of technologies that are focused on long-range communication with low power consumption. This makes a lot of sense in the context of remote sensors that do not have a lot of juice to operate, but you still need to have some kind of connectivity to work with them. There are other similar technologies like Sigfox, NB-IoT, and LTE-M, and those are very similar to LoRa. They have different characteristics, but overall, all those come to solve the same problem. Among other benefits, one of important one is the low subscription costs. So basically, if you have a 4G chip, it's fairly expensive to use the bandwidth. LoRa solves this problem quite easily. So the market is growing. This slide is a bit old, but more and more we can see that this technology is used all around the world to solve a number of problems. The Asia Pacific is the biggest adopter in this technology, and the industry that it seems to be more fitting is utilities. Like you can think like the gas meters or water meters in the houses have to be accessed by an individual to see the values. Now we can change these meters with this radio technology and be able to receive these values quite easily. So for these industries, this is quite appealing. So to discuss a bit about some applications that are out there in the wild, for example, in Japan, Michigan is using Sigfox, and they are changing about 805,000 gas meters. In Germany, DHL is using 100,000 roll cages. In France, they're using operators for LoRa for smart meters. In Brazil, they're using it into Max trucks. Over 1 million trucks are retrofitted with LoRa sensors. In China, they're using NB-IoT for electric bikes, and in Sweden, they are using it for smart electricity meters. Overall, we will see that basically these sensors are used to locate moving assets like vehicles, or as we said, to measure stationary sensors that are basically large in number, so the cost to access them is quite high. So, as we said, the LoRaWAN is in the LoRa power wide range category. The main point of the design is to be operated by a battery system, so it basically can consume very little power. There is the caveat here that the rate of data that can be communicated is very low. But in a sense, this is not a problem, because this is applications where you have to communicate this information very rarely. So let's say if you do a measurement for a gas meter, you don't have to do it every second, but a few measurements per day or within the week are more than enough to communicate what exactly you need. The main features that the technology targeted to solve when it was installed was to provide bidirectional communication. So you are able to communicate with the sensor and the sensor back to you. Although this configuration can be adjusted according to your needs, you can skip one of those communication channels, so the sensor can communicate only to you to save battery. It was really important for them to provide end-to-end security. So there is an authentication mechanism with the LoRa devices, so you can set it up with proper encryption, so no one can eavesdrop the communication and understand these values. And of course, to solve the main problem, we have to provide mobility and localization services. A bit about the architecture. The architecture is fairly simple. You have devices that have the LoRa chip, or for other technologies, similar chips. And the point is that there is a special gateway that can receive those packets. And the job of the gateway is modulate and demodulate the specific signal to these devices. So basically, you can place them wherever you want. You have to have the gateway. And from the gateway, everything else is conventional IT. So you can have whatever technology you need. The last point, the end point from the service side, is an application server. The job of the application server is to the decryption part of the information, and also to parse the data and provide them as a service. So between the devices and the application, there is no way to identify the information. The gateway just does part of the checking of the demodulation, like a CRC check or something like that. But the main thing is that this is the security that we're talking about. There is no way to eavesdrop this traffic. So what we wanted to do here, we know that these sensors are appealing also in other projects. For example, we know for a project that is a gas pipeline that is distributing gas in very long distances. And in this scenario, what's happened is that you want to have some kind of data be communicated between you and this gas pipeline. So the setup didn't have any critical data, because LoRa is not to be used for time critical information, but it was for weather data or localization data or information that were supportive to the whole operation. So what we wanted to do here is try to disrupt this, and we try to understand how we can break the protocol in a way that this information will not be available to the stakeholder. And we wanted mainly to focus on the practicality, how possible it is without breaking the world, how possible it is to make this information unavailable to the interesting parties. So what we focused on was basically two strategies. The main first part is to be able to find the sensors. So that was important because we're talking about radio signals. It was crucial for us to be able to understand exactly where are these sensors located, and how we can detect them. If you have a pipeline, the measurement, if I recollect, was about 2 to 3 kilometers per sensor. So you can imagine that it's difficult to pinpoint exactly where the sensors are if you do not have a mechanism to find them. So that is the first part that we focused on. And the second part was to disrupt it, to be able to make so that the sensor will not be able, or at least its signal will not be able to be demodulated by the gateway. The point is here simply to just drop the packet, not impersonate it and not replay any information. So for this project, we focused a bit on the equipment and we wanted to do something fairly cheap. We didn't want to invest a lot of resources. Of course, if you are able to do it, you can expand this project in a lot of ways. But we just use basic out-of-the-shelf products. We used an SDR like a RF. Basically, it's a module that you can program it as you wish to demodulate and modulate any protocol, including LoRa. So basically, you can do that and you can tickle part of the demodulation so that you can be able to send non-compliant packets. The idea here was to be able to receive and to set packets at the same time. We use the SDR in this context for the disruption part because the complexity of the programming here could not be done with just a simple LoRa chip. So we could take a chip and try to program it to do the stuff we wanted, but the context here was to be able to do more than that. So we needed to have such a device. For the localization part, for the gateway, you used an Arduino. It was fairly simple to program in such a way. The goal of this device was just to be able to receive data and try to calculate, to measure, to give us information as to where the sensor is. That was also a critical part of this process because we wanted to be as close to the sensor as possible to try to exploit the operation. So the localization basically is focusing on basic physics here. Each LoRa is emitting a signal to be able to communicate with a gateway, and that of itself is communicating some information. Even if the signal is encrypted, we can derive a few stuff. One of the stuff that we can derive is the power of the signal, how strong or how weak it is. Another thing is the timing, when the signal is triggered. All this stuff is information for us that we can use to understand where is the possible location of the signal. In this context, we use the power of the signal to be able to estimate the distance of the sensor. So in a sense, we make an assumption as to where it is, given the provided the signal we receive from the sensor. And the metric we used for that is the RSSI, which is the received signal strength indicator. This is a value provided by many other signals like the Wi-Fi. So the RSSI is basically a measurement of the power of the signal. It is used to indicate how good or bad is a wireless connection. And it's received in milliwatts measured by decibels per meter. And the point here is that we can use this information to get an estimation of how close or far away is the sensor. For LoRa, there is a range from -120 to 0, with 0 is the strongest possible value. So this is enough to give us some information about that. The issue that we got here is that the accuracy is not great because this signal is easily disturbed, as we will see, by a lot of factors, environmental factors. But in this context of 2 and 3 kilometers of distances, we do not need actually to be like 1 meter next to the sensor. We have to be maybe a few hundred meters. That will be more than enough to initiate the next stage. So there are other ways to do this technique, to localize it without using the received signal sensor. That would be timing calculations, but they require more equipment and more complex algorithms. So in this context, we wanted to keep it as simple as possible. So the RSSI basically can be provided by a mathematical formula. This is the formula shown here. Basically, this formula gives you the distance compared to the RSSI, and it's measured with two other unknown variables. That would be A, which is the received power that will be given by the sensor in 1 meter, and the other is N, which is the loss parameter or loss exponent, which depends on the environmental conditions. Now, for the same chip, A is going to be more or less stable. The problem is N, that is how the N fluctuates according to the environment. And we got a lot of problems with this parameter because it's fairly different if you have the sensor in a building, in an urban or in a suburban area. So it wasn't the most convenient formula to use. But under specific conditions, you can make a few assumptions about it. Like if it's in the open area and under specific terrain conditions, you will get more or less accurate enough values to give us results that we like. So this technique will not work probably at all in a closed space, or if there's a lot of buildings, or if you are not in a proper elevated position. But for this context, remember pipelines, long distances, open areas, this is more than enough. For our experiments, we calculated some values. These values were calculated after experimenting different distance areas using an outdoor environment. These are approximations. They will not work out of the box for every configuration, and they are highly tied with the chipset that is used in LoRa. But the experiments show that you can make good estimations about what is the possible value that can be given here. So the point is now that if you imagine, if you get one measurement out of nowhere, assume you get the distance from this mathematical formula. This is not enough, because basically you are placed in a point in space, and then suddenly you get a signal from somewhere, and you derive that, okay, this signal is about 0.5 kilometer away from me. The problem is you don't know where. Okay, it's a direction in a circle around you that you can understand exactly which is the location. So the solution here is a simple geometric problem. You have to use a trilateration algorithm, which is basically a geometric technique to find all the points given that you have a measurement for a sample. So what you have to do is to make multiple measurements. And in theory, if you make 3 of them in different locations, and you have three different measurement points for the same sensor, you can more or less calculate where this is coming from, because all these points, if are considered to be the center of a circle, will have one common dissection. So they're gonna connect in one common point. And this is the point where the sensor will be placed. Even if there is some deviation in the erroring of the calculation, it's going to be in an area close to this point of measurement. As more as measurements you can make, the average calculation is going to be more accurate. If you can take 10 or 15, no one is blocking you to make as much as you want. So in a graph representation, this is how it looks, and it's very simple. You're going to do the measurements in points L1, L2, L3. Every point is going to give you a distance. And then to the point of the dissection is going to be when the location of the sensor is. Again, the problem here is that if D1, D2, and D3 are not accurate because the formula was not correct or something is off, you're going to have a misapproach in where exactly these points connect, if they connect, because they can be smaller and there are no connections at all. Again, we solve this problem by making multiple measurements. So we tried this in Genoa. We went to the outskirts and we tried to do the calculation in the GPS coordinates. We try to use the suburban area and the urban area. The urban area did not work very well, but in the suburban area we had good results. Basically here we show the 3 measurements we take. The accuracy was more or less to the point, so we were able to locate that the sensor is indeed this place. And we just moved around these locations and we make the measurement multiple times in the same spot to be sure that the value for each distance that we get was as accurate as possible. Again, it's important to mention that this will not work, did not work very well when we were in the city or if we were in a closed spaces. So good. If you do the calculation, you can locate the sensor. So the next stage is to be able to interrupt the signal, and the rationale here is to lead the gateway to a DOS state. So what we want to do is we want to send a specific signal that is going to block the gateway from receiving the legitimate signal coming from the sensor. And so the message will be lost. So the idea here is just to do a common DOS state attack. The problem that we have with classic radio jammers is that we thought about, okay, you can go there and you can open the switch and you can just start jamming the thing out. But they are quite noisy and they disrupt everything in the vicinity that's in the same frequency. So basically, we didn't like it because they are controllably disruptive. And they have a lot of noise, so they are detectable. So someone can easily follow back to you. And there is another problem that LoRa is basically using a technique to hop frequency. So it's not going to send a packet in a specific channel, but it will deviate according to the implementation in a pseudo-random way. And in the EU bandwidth of LoRa, they have 10 channels. So basically, if you're lucky, you can disrupt only one of them. So that will be, with the probability counting, one packet per 10 packets that the gateway drops. And we really didn't like this kind of fault. So we want to improve a bit our approach here. So we did something kindly more selective. What we tried to do was basically the following. We tried to activate the jammer only when the reception of the packet is going to happen. So one thing about these sensors is that usually they are having a predictable pattern as to when they send the packet. So they're going to send it every, let's say, a couple of hours or every couple of days. So usually this timetable is very, very specific. So one thing that you can do is you can activate the sensor when the packet is leaving, or deactivate it when it's not to be used. The other thing that you can do about the channels is that you can create multiple configurations of the same jammer. So basically, you can put 10 filters that are gonna look at all the channels in the LoRa frequency, and you can activate them all at the same time with the same rationale. The other approach that we investigated and we implemented here was actually not to time the LoRa packets, but basically wait for the packet to be sent by the sensor. And the moment that the packet is transmitted, immediately we send our jamming packet. So basically, we wait for the sensor to start communicating by its own. And when we detect this interaction, then we send the signal. And our signal is basically just a burst of energy. So it's a high power signal in the same frequency, in the same modulation, that what it's going to do is going to disrupt the legitimate message. What this creates is basically, from the whole information that's communicated, part of the packet is lost. Part of the packet is destroyed in the process, and this results in invalidating the CRC of the packet. So what we managed to do in our lab is that every time a packet was sent, we will do that, and the server, the application server that we mentioned before, will not receive the packet at all. Or if it will receive the packet, it will complain that the CRC was false from the gateway, and it will drop the packet. So in a sense, we were able to do that in a very simple classic way, but we just did the extra step of trying to activate the jamming as less as possible, so that it's not visible to any defense features. A bit about the implementation. Everything was done in Python using GNU Radio in the SDR. We had a few problems with that because Python is slow, so these kind of techniques and modulations have some performance. They have a lot of performance demands. For the project, it was very good. It was surprisingly very effective and much simple to do. But it would be much better if you upgrade this implementation to a C kind of style. But for this implementation, Python can work very well. And here is what we could see from the GNU Radio is like when the LoRa packet starts. You can see in the first screenshot, the signal is captured by a detection system, our detection up to the SDR. And then what you see in the picture below is what happens when we send the burst of energy. So basically at this point, information has been distorted. Even if you change a few bytes or a few bytes from the whole transmission, the CRC is going to fail. So you don't have to do a lot of stuff to actually block the signal. So that seems to be quite an effective way to go on with it. So the final problem that we have was, okay, we were interested to see how this is going to play out, but we really wanted to see how realistic is this in the real world, and having to see how we're going to execute it in a pragmatic way. A thing is that for these distances, to do it actually, there is a lot of overheads. You have to move long distances, so probably you need a car, you have to go around, you have to stay there for hours to do these measurements. So we thought that this is not probably that can be executed in a fast pace if you want to do this kind of analysis. And we thought that maybe it's better to go with something more elaborate. Another thing is that those limitations we have other limitations that have to do with the terrain. So basically, if you are behind a hill, or if you have a lot of trees, or if there are buildings in front of you, all these measurements for the distance, for example, would be problematic and misaccurate. So we'll have to think about that. So as we moved on with the terrain problem and the selected jamming approach, we considered these factors, and we understood that a good way to solve the terrain problem is to be elevated. So we have to be either in a high terrain or high elevation to understand, to have a better reception of the signal, and also have a most clear reception of the signal because of all the interactions that the signal might have with terrain. And also be better for us to be more effective in our jammer, because the jamming module has to be relatively close to the sensor to be successful. So to do that, we just thought, okay, why won't we use drones? Drones are fun, and they are easily controllable, and they are cheap right now. They start to be becoming better and better in battery consumption, etc. So we thought that if you are elevated in 20 or 30 meters in altitude, away from any discrepancies, you can easily make these measurements. Well, easily, you can make these measurements with not a lot of misaccuracies. So we observed this difference in ground elevation, that in the ground, basically, we will get a lot of fluctuations, but in terrain, we will get more static values of the RSSI. So that was, for us, a good solution, and it seems like drones are very good to travel easily these distances if they have a lot of power, of course. And we thought that that might be a nice way to actually make this approach pragmatic. So here the rationale was very simple. We just take the drone, we select a location close to the facility. We say here that could be a 10-kilometer radius, but we're more or less guessing about 3 to 4 kilometers around the area. And at this point, what we'll do is that we will activate the drone, take altitude, and try to make a measurement for the RSSI. And here we did this fairly simple with just a Raspberry, a battery, and some Wi-Fi connectivity with a mobile phone. So we were able to get these values with this method. The measurements that we have to take for the SSI have to be a lot. So we did 4 or 5 per location, just to be sure. 4 or 5 is the number that we gave here, but in another location we took 10 times that number. So we want to create an average between those values per location. After that, you have to move to 2 more locations. That is to create the circle pattern that we described before. Of course, you can make more. You can make 5, 6, or 10, or whatever is available under your resources. And all this information gonna guide you to make the correct measurement for the LoRa sensor. After all this process, we calculate the location of the sensor. So that could be on average in a few hundred meters far away from the sensor, which is fine. It's more than enough for us. And then we will move close to it to try to exploit it. So yeah, the approach sense is the next step, that we approach the sensor and we try to activate the jamming attack. At this point, we will just put the drone to the ground, and in our experiment, we just let it in the ground, but what you have to do is to just levitate it again and then have the better signal reception. And then we will do the trick. When the packet will be emitted by the sensor, we will instantly send a jamming signal back into it so that we can make sure that the perception will not be received. So I have a video for you, which is how we executed this. It's like, this is in the outskirts of Genova. So basically, we wrapped up inside the drone the gateway. We had a lot of troubles with the weight for this guy because these guys cannot take a lot of weight. But it's because this is not one of the most expensive ones. If you get to the higher end drone, you can definitely put a lot of equipment on it. So at this point, we are moving the sensor to a specific location, the drone to a specific location. This is coming from a pilot, so we are not allowed to fly these things without an authorized guy. But everything could be automated if you have the license or not, anyway, to do so. So the pilot was not a necessity. Just for legalities, we have to have someone authorized to fly the thing. The measurements were in these 3 locations that you see in the map. Basically, we knew that the sensor is in the red spot, and we have these 3 points. And now the green spot is where we took the first measurement. So it's fairly close to the sensor, but the point here was to understand even if this value was good enough. So we tried to elevate it in different altitudes to see the measurement that we got, how good or bad will be these values. We seems to be that for the specific limitations that drone had, we get on average good values on the 20-meter range. And how it works is that we will get these RSSI values from a measuring point. You could see that there are fluctuations at some point in the first measurement, but then stabilize to another value. And what we do is that we will put this for a lot of values to create an average perspective or what to be the correct RSSI value. What we have also is the latitude and longitude using GPS. We can use that also to understand where is the drone. And then what we would do is we will go to the next location. So the point here is that this drone was be able to fly for 20 minutes. So it's not something that we can use for actual long distances. But all those are limitations of resources and nothing more. So if you have more powerful devices, you can easily do these measurements for long distances. One of the problems that we find out in the second location is that if you have a mountainous terrain very close to you and you don't go above it, you will get completely disrupted values. So you have to place it a bit strategically in the air. And then the drone moved to the final location, which was the third point in the map. For us, in this scenario, 3 locations were enough. The approximation here was about 100 meters in the proximity of the sensor. So that was more than enough to consider it as a success. But as we said, this kind of calculation will be vastly different if you try to do this in a more complicated terrain, like if you do it in the city, basically because there's a lot of disruptions there, etc. So at this point, the drone presumably has located the sensor, and now it's going to try to disrupt it, to jam it. And how we'll do this is that we will wait the signal, and then we're going to send the burst of energy that's going to disrupt the process. So basically, what happened in this experiment was that the CRC was corrupted. So the signal actually reached the application server, but it could not be used by the server. So it was dropped out and was thrown away. Importantly, in this scenario, the disruption lasts 5 seconds. So we just click on the jammer for 5 seconds every time this jamming has to happen, and then we switch it off. And as I said, the channel hopping was tackled by using multiple modules of the same feature. Okay, so overall, we are happy with these results. We think that this application was fairly easy to follow up because it didn't take a lot of resources on a lot of expensive equipment to pull it off. The main thing that we think is the next step is to just use something more quality for the localization. We're thinking to move over time, difference of arrival. And the main limitations that we have was basically the drone. So the drone couldn't lift the weight. So if I remember correctly, it was like 1.5 kilograms, the full equipment, and the drone could do less than 1. So we have to do a lot of tricks to be able to pull this off. But a good drone that can lift this kind of stuff is on the 5K range. So it's basically how much resources you can put into this issue. And the other limitation was legalities to flight. Basically, you have to be outside the city in a remote area with an authorized pilot. And of course, those limitations do not concern an APT or any other threat actors. So the point of this talk is that we see that there is a lot of advances in these technologies in LoRa and the IoT world, and we see that there is a desire also to try to break them. So there is a lot of ways to do that, but as we move on, we can see that those idiosyncrasies that they have on these distances or whatever we have to do that, or how much time do we need to waste on locating the sensors, slowly can be changed if you use the correct technology. And here, drones were a good way to solve very pragmatic problems, like how to reach the sensor, how to use techniques to locate them efficiently in a fast way. And this highlights that slowly you have to consider the physical and regional security of your equipment. Like, okay, so it's not like a drone will fly to you with a bomb, but it can be like fly close to you, disrupt you, and then go away, and you have no idea what happened. So we think those are issues that maybe the industry should have a look around in the following years. And that was my talk. Thank you very much.
Thank you so much, Yiannis. Thank you so much. It was very interesting. So we just have one quick question,
Sure.
which is if you have read in the news of any attack, not exactly like the one that you described, but attacks performed by the use of drones, cyber attacks.
So as we look at this project, I would say the answer for now is no, as far as we know, at least. What we know is that they have been used for resonance, for military purposes and other reasons, but I haven't seen someone weaponizing the drone with a jammer or stuff like that and actually using it in the real field. The reason why we mess with drones was because they can easily reach utility locations like power grids or other infrastructures, and is considered we already have these limitations or defense mechanism against drones, like they cannot fly close to the airports. So the industry is slowly is a bit concerned as to what will happen if a drone reaches my infrastructure, what it can cut a cable, or if it can do stuff. Even in this scenario, the idea was, okay, it can just have an antenna and create problems to you. But there's no an event that is validated by the industry that I know of.
Okay. Thank you so much again, Yiannis.
Thank you so much.
Thank you.
Have a nice day.
You too.